Now let's go to another beautiful topic. It talks about is also under current electricity. You understand? It's also under current electricity. We're looking at what we call Ohm's law. This particular person is a what? Is a well-renowned scientist which came up with what? Such definition, which is still helping scientists up to do what these days practices. Now, the electric current flowing through what a metallic conductor wire at constant temperature is directly proportional to the potential difference across the two ends. Now, the current, it says the electric current is directly proportional to the potential difference. Are you getting it? So that's your V as R. So if your constant of proportionality, by the time you remove it, you are equal to your R. You understand? So your R, which is your resistance, will represent your constant of proportionality. So that is for your R. So therefore your V equals IR. Equation 1. Hope you are saying it. So it's as simple as ABC. Now let's proceed to resistance in parallel. Resistance in parallel. Under resistors in parallel, we spoke about how they are actually being arranged. When you have something like this, these are resistors in parallel. How do you arrange them out? So if this is R1, your R2, your R3, how do you get them out in terms of what? Total resistance. So your total resistance will be your R1, R2, R3, all over your R1 plus R2 plus R3. You can see that will be the what? Actual formula whenever you are calculating your resistance in parallel. Let's proceed. Factors affecting electric resistance. Factors that can affect your electric resistance. We said it the other time, we said the restriction of flow, of flow of electron in a what? In a metallic conductor. When there is a restriction of flow of coin in a metallic conductor, we say that such metallic conductor is experiencing. So any particular material which has the influence on what? Free flow of what? Charge. We say that that material has what we call resistance, high resistance. Now, under the factors, number one, the length of your wire. I remember this particular question twice in the O-level which I wrote. I've always been meeting this question. The question goes like this: write out factors that affect resistance. Let's put a drawing so that you can understand. If this is a metallic wire. Now, what are the factors that affect what? That affect the resistance of this conductor. I told you that this is free flow of electron. Now, when the material is not allowing a free flow, we say that that material has what we call high resistance. You understand? So we are looking at resistance in this case. Now, what are the factors that can now affect that resistance? Number one, the very number one factor is the length of the wire. Number two, what we have there is your cross-sectional area. I thought I would explain what is meant by cross-sectional area. Now, the bigger this cross-sectional area, that's this circle here, the bigger it is, the more resistance will be what? Restricted. Will be experienced. The more current charge will be what? Restricted. Bringing about your current resistance. Hope you are getting it now. Now, apart from that, we have what we call temperature. If I were you, I will what? I will note these 3 points powerfully. I will note them down in a place where I will never forget. Write out the factors that affect resistance. So we mentioned 3. Now the very last one is the what? Nature of material. Nature of what? Material used. Hope you are getting it out. So those are the 4 major factors that affect your what? Resistance. Now let's go to another beautiful one. That's what we call Wheatstone bridge. Now we are going to be looking at what a Wheatstone bridge means. Under a Wheatstone bridge, what do you have? A Wheatstone design bridge circuit, which gave an accurate method for measuring what? Resistance. It's not that you can't measure your resistance with what? The other measuring instrument which you use to measure resistance. But if you use your Wheatstone bridge, most times the results are always what? Accurate. If you have a circuit here now. This is a typical example of your what? Wheatstone bridge. If you have yours break down this way, now it comes here, you have one like this. Anywhere you get to see this structure is called a Wheatstone bridge. Now I'm drawing it out here so that you'll be able to locate it anywhere you have. It's going to be very, very much interesting for you to actually know. Now this is how it's being labeled. You have your R1, R2. You have your R3, R4. Now, if this to be a Wheatstone bridge, you now have our battery here. You understand? Now, at this point, all these points are actually being labeled. Now, within here, we have what we call your galvanometer. What does the galvanometer do? It helps to measure what? The voltage that is being experienced in this circuit. Now, you now label this point C, point A, point B, and point D. The mathematical formula you now use in the Wheatstone bridge is this. You just take the division of these two sides, as your R1 over R2 equal to what? R3 over R4. That's the formula you'll be using in your Wheatstone bridge. Meaning that I can decide to give you 3 different resistors. You understand? If I give you 3 different resistors, you can definitely check for the last one. If I also give you the upper 3 resistance, you can also check for the what? The lower resistance. What do we intend to achieve? I said it initially. I said the Wheatstone bridge most times is being used to what? Obtain the most accurate value of your what? Resistance. So let's go to another good device. We talk about that's your what? Potentiometer. A potentiometer consists of a uniform resistance wire AB in the diagram below of 100 cm. Now a source of EMF E and maintain a steady current I in AI. Since the wire, if you look at those stories there, you realize that we first of all defined what a potentiometer meant. Now the potentiometer consists of uniform resistance wire AB in the diagram below. Now if you look at the diagram, you realize that this is just a typical diagram. Let me just draw one for you. Now if this is to be the diagram, initially the length of this is your potentiometer. Maybe the length is 100 cm. Now at this 100 cm you have EMF. There is an EMF for EMF 1 for full length. There is also an EMF for a very short length. You understand? So if you have another EMF here, which is EMF 2, EMF 1. Now this region we have the length. That's your L1 and this will be your L2. Hope we are getting it now. So these are the major values that will be given to you. 2 lengths. The first length is for the full length of the material is 100 cm. While the second length will be given to you. You understand? And you have to obtain any of the 2 EMF. This is what I'm saying. E1 over what? E2 equals L1 over L2. This is the strategic formula used in your what? In your potentiometer. You understand? There are some examples there which, because of our time, you'll not be able to break it down completely. By looking at Kirchhoff's law, you have to know this law. So under Kirchhoff's law, we have some terms we need to know. There are some terms you must what? Understand. Number one of them is what we call a node. What is a node? Number two, the second point you need to know is what we call a loop. The third thing you need to know is what we call a loop. These are terms that you need to know when it comes to Kirchhoff's law. We spoke about Kirchhoff's law. Under Kirchhoff's law, we'll be looking at these terms, for us to have a clear understanding of those terms before we now go into Kirchhoff's law proper. 2 laws you need to know. There's what we call Kirchhoff's voltage law, and there's what we call Kirchhoff's current law. So those two are what we are going to define. But before then, we are going to look at these terms one after the other. Now, as regards the node, let's look at a node now. Or let's just say node. What is a node? Now, from our definition there, we realize that a node there says that it is a point. Look at, when you say a node, it is a point in an electric network where two or more connections meet. You know, when I say connection, if this is to be a network, you know, in electronics or electrical engineering, they make use of circuits a lot, where there is combination of or connection of what? Wires. This could be a wire. You understand? It could be a cable. Whether it's cable, whether it's wire, it's still a metallic conductor. Now, it can interconnect a lot of things. It can interconnect resistors, it can interconnect inductors, it can interconnect capacitors, depending on what you are trying to drive at. But the point at which they all meet matters a lot. Let's say this is point A, this is point B, this is point C, this is point D, this is point E, and this is point F. Now, we look at all those points. The point where two metallic conductors meet, you know, these points now, if you look at it, is consisting of 1, 2, 3. You understand? So this point is what we call a node in your electric circuit. The point at which two or more electric materials meet. You understand? If you look at that, it is the point in an electric network where two or more connections of wire meet. That is, those wires that conduct electricity, two or more. You understand? The point at which two or more wires meet. This is a node. Perhaps how many nodes do you have here now? It's just 6. This is also another node. 2 wire. This 1, this 2. This is another node. This 1, this 2, and this 3. This is another node. This 1, this 2. You understand? So the point in a particular network where two wires meet, you understand, is called a node. What is a loop? Now, it is defined as any close connecting